podcast is brought to you by LMU Munich.
Well, good morning, colleagues and friends. We are happy to start the morning session with Ji Yin from Harvard, talking about high-spin holography.
Thank you. I'd like to thank the organizer of the conference for letting me to give this overview talk about higher-spin gauge theory and its role in holography. It's a tremendous pleasure for me to be here and speaking about a subject which I've only worked on for a short amount of time. And I should also apologize for that. I'm going to be talking more about the issues and questions I've thought most about, and this talk is probably going to be far from a fair and balanced summary of many of the recent exciting developments on the subject, but I'll do what I can. So let me begin with a little introduction. We all know that string theory, the spectrum of string theory involves an infinite tower of massive higher-spin particles. In the high energy limit, or equivalently in the tensionless limit of string theory, these higher spin particles behave like massless particles, and it's natural to suspect that perhaps there's some emergent higher spin gauge symmetry in the high energy limit of string theory. Now, this idea has been around for a long time, but it's never been really made precise for string theory in flat spacetime. However, it can be made precise for string theory in ADS space in a way I'll explain later. Now, the study of interacting theory of higher spin gauge fields goes back a long time. Of course, in the real world, they are composite massive higher spin particles. It's not hard to write down effective theory of interacting massive higher spin particles. But it appears to be much harder to write down interacting theory of massive higher spin particles for some good reasons. There are no-go theorems. For example, Weinberg gave a well-known argument that if you study amplitudes with soft emission, with emission of soft masses, say higher spin particles, such amplitudes are severely constrained by Lorentz invariance that it essentially forbids any kind of non-trivial amplitudes involving interaction of masses higher spin particles. And then there's the Weinberg-Witten theorem, which says that you cannot construct gauge invariant stress energy tensor out of massless particles of spin greater than 1, which prevents you from at least minimally coupling higher spin particles, higher spin fields, massless higher spin fields to gravity. And then there's the Coleman-Mandula theorem, which says that there's no conserved higher spin charge, assuming that you have non-trivial S matrix in asymptotically flat spacetime and a mass gap in the theory, which essentially implies, or equivalent to a statement that the theory is IR-free, or that the interaction is local in some sufficient way. Now, these no-go theorems make certain assumptions that is sometimes possible to evade. For example, say the Weinberg argument essentially assumes minimal coupling of the higher spin fields, and this need not be the case. And also, in these kind of no-go theorems, it's often assumed that interaction is local and that there are finitely many fields, which may not have to be the case. In fact, it is possible to write down explicit gauge invariant, well, at least up to cubic level gauge invariant interaction vertex of higher spin fields, even in flat space-time. But these will necessarily be non-minimal coupling in that, say, you take a triple of spins S1, S2, S3, and it turns out the gauge invariant cubic vertex, gauge invariant with respect to some suitable nonlinear higher spin gauge symmetry would involve n derivative interaction, n derivative coupling, where n is bounded from below by S1 plus S2 minus S3, where S3 is the smallest spin out of the three. And for S1 or S2 greater than 2, these couplings are going to be non-minimal. Now, the implication of this on interaction of higher spin fields in flat spacetime is not entirely clear, because even if you can construct the cubic coupling, it doesn't guarantee the existence of non-trivial S matrix. I'm not going to go in that direction. Instead, I'm going to be talking about another way to avoid these no-go theorems, which is to talk about higher spin gauge theory in ADS space. In fact, in retrospect, we know from ADS CFT that interacting theory of higher spin gauge fields in ADS space must exist because in examples where you have some gravity theory in ADS or string theory, this is dual to a large N gauge theory, in the limit where you turn off the interaction of the large N gauge theory, there are conserved higher spin currents in the free limit of the large N gauge theory, and these conserved higher spin currents are going to be dual to higher spin gauge fields in bulk ADS. This has been pointed out more than a decade ago by many authors listed here, it was thought that the tensionless limit of type 2b string theory, or perhaps more appropriately, string field theory in ADS 5 times S5 reduces to a higher spin gauge theory in the tensionless limit. This is a rather complicated theory. We don't really know very much about the structure of this higher spin gauge theory. It is coupled to an infinite tower of massive matter fields as well. But in fact, long before the discovery of ADS CFT, people have already constructed fully nonlinear interacting higher spin gauge theories in ADS. In 87, Fredkin and Vasiliev wrote down cubic vertex for gauge invariant cubic vertex for higher spin field coupling in ADS4. And this program of finding a nonlinear, fully gauge invariant equations of motion for higher spin fields in ADS was completed by Vasiliev in the early 90s. So Vasiliev's system describes the Vasiliev system is a set of equations of motion, fully nonlinear, for that describes interaction of higher spin gauge fields in ADS4. I'm talking about the most standard Vasiliev system here. The theory consists of a single tower of higher spin fields of spin 0, 1, 2, 3, etc., all the non-negative integer spin. The theory also admits a truncation to what I would call the minimal bosonic theory, which includes only the even non-negative integer spins, but no further. This Vasiliev's construction is based on a frame-like formalism. So the equations of motion are written in first order form, even though they are in principle equivalent to the standard form of equation of motion you would like to write, which is the form box acting on the field is equal to some nonlinear terms. But it turns out to be most concise and convenient to formulate this theory in the first order frame-like formalism. The cleverness of this formalism also has a disadvantage, which is that it doesn't tell you immediately what the Lagrangian is. I see no clear obstruction to finding a Lagrangian for the system. One can in principle try to recover the ordinary Lagrangian with a second order kinetic term plus nonlinear terms, order by order in perturbation theory, but that is, has not been done explicitly. This issue is not a problem if you want to compute tree level or say correlators in ADS, but it is a priori an obstacle to quantizing the system. Now, the role of Vasiliev theory in the context of ADS CFT correspondence was clarified by Stetsky and Sandel and by Klebanov and Polyakov in 2002. In particular, Klebanov and Polyakov made the following key observation, that is, the holographic dual of a pure higher spin gauge theory, by which I mean the theory like Vasiliev's system involving only higher spin fields and no other massive matter fields, is going to be, the dual is going to be a large N vector model, as opposed to adjoint type gauge theory. I will elaborate on this in a moment. And also, by changing the boundary condition on the fields in ADS, the same higher spin gauge theory in the bulk could be either dual to a free theory or an interacting critical theory. So now I'll say a few more words about this duality between higher spin gauge theory and vector models in ADS4 CFT3. So a little bit of brief recap of Vasiliev's system. the system was formulated by writing down, packaging all the physical degrees of freedom into so-called master fields, which I denote by A and B. These master fields depend on the space-time coordinates x mu, as well as some internal twister variables. This is a misspelling, it's a twister with O, which I call y and z. One defines a star product on the functions, on the space of functions of these twister variables y and z, schematically of this form. This star product is only going to be needed to write the equation of motion. The equation of motion for Vasiliev system takes a deceivingly concise form in this formalism. It says that the field strength constructed out of this one form, master field A, which is a one form in X and this internal twister space, with A regarded as a connection of the star algebra, the field strength 2 form constructed out of this one form A is related to this scalar master field B in this way. This is kind of a concise but yet obscure way of writing the equation of motion. Let me just point out that the left-hand side is a 2 form in X and Z space, whereas the right-hand side only involve dz squared and dz bar squared, so it's kind of a constrained system. And this k and k bar are the so-called Kleinian operators, which are can be written down as explicit function of y and z that obeys certain property, which I will not need for now. This function f of b star k is a star function. That is, you take some ordinary function with some Taylor expansion and replace all the products by star products. This will be this function f of b star k is going to be important later. Now, okay, so the role of this function f of x that appears in the Vasiliev's equation, it turns out that up to field redefinition can be put in the following form. F of x can be put in the form x times e to the I theta of x, where theta is a real and even function. As a Taylor expansion of this form, theta naught plus theta 2 x squared plus theta 4 x to the fourth plus dot dot dot. All these coefficients are a priori parameters that controls the coupling or interactions of Vasiliev's theory. So there's some kind of freedom that is allowed. But still, the system is very much constrained. In fact, for instance, theta naught only controls cubic and higher order interactions. Theta 2 only controls 5th order and higher order interactions, and so on and so forth. Let's say if you're interested in computing a tree-level 3-point function in the bulk, then only theta naught will enter, as well as the overall coupling which drops out of the equation of motion. It turns out that if one insists on having parity invariance, then the theory is very much constrained, that is almost uniquely determined up to the overall coupling constant. That is, there are only actually two possibilities for this choice of function f of x, and the resulting theories are called the A-type and B-type Vasiliev theory. The parity dividing theories would allow the more general f of x, which will be, which have a much richer structure. The Vasiliev's equation was written down in a background-independent formalism. It wasn't obvious a priori why it described a theory of higher-speed fields in ADS4. In fact, to do perturbation theory, one has to first start with a vacuum solution that is of the following very simple form. W and S are the Z and X and Z components of the one-form master field A I wrote in the earlier slide, and the scalar field B is set to 0 for this ADS vacuum solution. The W0 is some function that's quadratic in the twistor variables y that is constructed out of the spin connection via bind of ADS4. Its precise form is not going to be important for me at the moment. The fact that this thing is constructed out of precisely the spin connection via bind of ADS4 is such that it will solve Vasiliev's equation in this special case. Given this vacuum solution, it turns out that if you linearize the Vasiliev's equation around this vacuum solution, then one can show that the linearized equation is equivalent to the standard Franz-Stoll equation or standardization for free higher-speed fields propagating in ADS4, which does come from a standard Lagrangian with a second order with 2 derivative kinetic term. Roughly speaking, at linearized level, this master field B contains higher spin generalization of Weyl curvature, whereas A contains what you normally consider to be higher spin gauge fields that is represented by a symmetric rank S traceless tensor. One can recover the ordinary form of the equation motion for higher spin fields, say box minus some mass squared acting on the field is equal to some nonlinear term, where this mass is of order ADS scale that is determined by higher spin symmetry. One can recover this order by order in principle from Vasiljev's equations by re-expressing the master fields in terms of the physical degrees of freedom. Now, let me just emphasize that the Vasiliev system described is a theory of classical interacting higher spin fields, gauge fields in ADS4. As fully gauge invariant, the interactions are highly constrained and almost uniquely fixed by higher spin symmetry, at least within Vasiliev's framework. In particular, this means that if quantum corrections to the theory respect higher spin symmetry, then there's not much freedom for the equations of motion to get renormalized. It suggests that the theory is perhaps renormalizable and even UV finite despite the appearance of arbitrarily high order derivative interactions and possibly non-local coupling in the theory. Now, if Vasiliev theory is indeed a consistent theory that includes, in particular, spin 2 gravitons, then it should have a three-dimensional gravity CFT dual by the standard philosophy of ADS CFT correspondence. This was proposed by Klebanov, Polyakov, and by Sezgin and Sandel in 2002 that Vasiliev's minimal bosonic theory, which includes the single tower of even non-negative integer spin fields, gauge fields in ADS4, is holographically due to the free or critical OM vector model. I'll elaborate on this on the next slide, but just to summarize the statement of duality here, the two types of parity invariant higher spin gauge theories, A-type and B-type theories, are due to the ON boson fermion theories, and depending on the choice of boundary condition for the bulk scalar field. The bulk scalar field is such that one can assign two different alternative boundary conditions. Both are conformally invariant. In one case, the bulk scalar is due to a dimension 1 operator in the large N limit. In the other case, it's due to a dimension 2 operator on the boundary in the large N limit. Depending on the choice of boundary condition, these A-type or B-type theories are due to either the free ON theory or the critical version of the ON theory. The ON vector model is something very simple. The free ON vector model is simply a free CFT of n massless scalar fields in 3 dimensions. Important thing though is that here we must restrict to the ON singlet sector in the sense that we're only allowed to talk about the spectrum and correlation functions of ON singlet operators. For instance, essentially all the single trace conformal primaries of this theory are conserved currents of the following form. It's a currents of some spin S, where S is an even non-negative integer that is bilinear in these n free massless scalar fields. The critical ON model, on the other hand, is an interacting theory. It can be obtained at the critical point of a double trace deformation of the free ON theory. Importantly here, for the purpose of holography, it's also important to restrict the critical theory to the ON singlet sector as well. This is needed for large N factorization, otherwise there will be no sense in which the theory has a weakly coupled bulk dual. The higher spin symmetry in the critical theory is broken by 1/n effects. It took a little while to figure out how to actually do computations of correlators in Vasiliev theory. In a couple of papers I wrote with Simone Giambi in 2009 and 2010, we computed the full tree-level 3-point functions of these high-spin currents using in a standard ADS-CFT sense in Vasiliev theory in ADS4. And show that they match precisely with 3-point functions, including all the coefficients with normalization with the free and critical ON vector model. So this is a non-trivial test of the precise higher derivative interaction structure of qubit coupling in Vasiliev theory. And now just to mention one point, which is that even though we didn't actually extract explicitly the bulk Lagrangian, we didn't actually need it to compute the tree-level correlator because using the equation motion is enough. If you want to compute endpoint function of the boundary, you regard n-1 of them as sources and solve for the n-1th order field that is comes out due to interaction of the field sourced by these n-1 sources and extract its boundary expression value, which is going to be proportional to the endpoint function. By comparing different cross channels, can fix the relative normalizations. Now, the tree-level correlators can in principle be calculated using just the Vasiliev equations. However, in practice, this is still quite hard. It took a lot of work just to get a 3-point function in the parity invariant case. The parity dividing case, which involved this interaction phase theta of x I mentioned earlier, is already much more subtle and is still a work in progress. The 4-point function computation explicitly, as well as loop corrections, has not been done yet. It will be very interesting to do them, but there are some technical difficulties that have to be removed before these can be computed. Now, in a very beautiful work by Malosina and Zhiboyedov, they show that from the CFD side, on the other hand, exactly conserved higher spin symmetry implies that the CFT is free in the appropriate sense. And now, I mentioned earlier that the critical OM model does not have exact higher spin symmetry. The higher spin symmetry is broken by 1/n effects. This is understood in the bulk as higher spin symmetry broken by boundary conditions. So even if you have a higher spin gauge theory in ADS, it does not mean that the dual CFT have exact higher spin global symmetry, because the symmetry could be broken by ADS boundary conditions, and it often is broken. Nonetheless, the broken symmetry still constrains the theory. For instance, it constrains the 3-point function of the CFT at large n. I think Huang will explain this later today. So the A-type Vasiliev theory, as I mentioned earlier, with what I call delta equals 2 boundary condition, meaning that the boundary condition assignment is such that the bulk scalar is due to a dimension 2 scalar operator of the boundary. The higher spin symmetry is broken. This can be demonstrated directly in the bulk. However, it turns out that one can show if the conjective duality between a free ON theory and A-type theory with delta equals to 1 boundary condition holds, then this analogous statement involving critical theory with the alternative boundary condition follows order by order in 1/n to all order. So combining this with a statement with the theorem of Malosina and Zhiboyedov, it almost proves this conjecture, except that what one still have to show is that a Vasiliev system can be quantized in a manner in which higher spin symmetry is not anomalous or broken by boundary conditions, which is not entirely trivial. Especially given that we don't know a very useful form of the Lagrangian of the theory. There's some alternative ideas that I should mention in deriving this duality, in deriving the bulk theory directly from the boundary ON theory from either collective field theory or holographic RG. Neither approach is complete at the moment. That one has not actually recovered the Vasiliev theory, but these are promising ideas, which we might hear more about. There's a large class of generalizations of these duality between higher spin gauge theory and vector models. Back 5 years ago with Davide Ghiotto, we showed that we argued that Chern-Simons matter theories provide a large class of interacting conformal field theories in 3 dimensions, and they often have supersymmetric or non-supersymmetric string theory duals in ADS4. It was soon realized, this was soon realized in explicit examples involving n equals 6 supersymmetry and semi-classical gravity limit in the bulk by ABJM and the work of many others. But in many other cases, supersymmetric, let's say, Chern-Simons matter theories, in fact, are always due to higher spin gauge fields in ADS, that there's no limit in which one recover semi-classical gravity. Chern-Simons vector models, this is a special case of the Chern-Simons matter theories, where the matter fields are in, say, fundamental representation of the typical Chern-Simons ON or UN gauge group. The Chern-Simons vector models it was realized in a couple of papers from last year that they, just like the critical OM model, have approximately conserved higher spin currents at large n. And it was then conjectured in this paper I wrote with Simone Giambi and Minwala, Prakash, Trivedi, and Wadia that the Chern-Simons vector models in 3 dimension are due to the parity violating version of Vasiliev theory in ADS4. So what's the Chern-Simons vector model? This is a generalization of the vector model I described earlier. In fact, in 3 dimension, you take UN or SUN Chern-Simons theory, or you can take ON, but I'll talk about UN for simplicity. You can couple these to massless scalars or massless fermions in any representation and get a conformal field theory. But here I'll focus on the case where the matter fields transform in the fundamental representation of the Chern-Simons gauge group. So let's say for the Chern-Simons fermion theory, the action takes this very simple form. There's no marginal operator you can write down that's gauge invariant, and this is a critical theory. In the boson case, it's slightly more subtle. There's a marginal 5 to 6 coupling you can write down in the case of Chern-Simons scalar theory, but there turned out to be a finite value of the 5 to 6 coefficients at a conformal fixed point that's controlled by the 12th coupling of the theory and the large n limit. So I'll be thinking about this theory in the large n limit, holding the 12th coupling n over k be finite, where k is the Chern-Simons level. This theory is interacting theory, and higher spin symmetry is broken. But it's broken in a way that's suppressed by 1 over n. In fact, one can write down single trace higher spin primary operators, which are not conserved in their interacting theory, which I call JS. However, in fact, just by applying the classical equation of motion, one can show that the divergence of this current, spin S current, or spin S primary operator, is actually a linear combination of some double trace operator constructed out of a pair of the currents, or triple trace operator. And one can show by matching quantum numbers on both sides that this relation holds a large n finite lambda in the quantum theory as well. So in particular, this means that the higher spin symmetry is broken, but it's only broken through the mixing of the divergence of the single trace current with multi-trace operators, which is why it's suppressed by 1 over n effects, or suppressed by 1 over n. Let me just mention that this theory is solvable at large n, infinite n, and finite lambda. For instance, essentially by applying a Schroeder-Dyson equation in Lycon gauge, which can be solved. So we did this. We computed the free energy of the Chern-Simons fermion vector model at finite temperature at infinite n and any arbitrary value of finite lambda as a plot of this form. So the free energy decreases for fixed n and increasing lambda at large n. It decreases with increasing lambda and goes to 0 at lambda equals 1. There's some explanation of that, which I will not elaborate on at the moment. This calculation was generalized recently in this work to Chern-Simons scalar theory, as well as the supersymmetric version of Chern-Simons vector model. By solving analogous Schroeder-Dyson equations, Arani, Ger-Ari, and Jacobi recently, actually last week, has computed 2-point and 3-point functions of a class of currents exactly at large n in these theories. I'll make a few comments on correlators, 3-point functions. In a paper I wrote with Prakash and Giambi earlier last year, we showed that 3-point function of conserved higher spin currents in 3 dimension must be a linear combination of 3 possible structures. That is, the 3-point function of the currents in free boson theory, the 3-point function of the higher spin currents in free fermion theory, or a parity odd structure that does not exist in free correlator, but exists in interacting theory. It was so we know that the 3-point function of the higher spin currents must be of this form with some coefficients, but we're not able to determine these coefficients. These were fixed by the work of Malsina and Zhiboedov through the study of slightly broken higher spin symmetry. They were able to determine that these coefficients are of the following form, of the form cosine squared theta, sine squared theta, and sine theta, cosine theta for some phase theta. This structure was also discovered earlier by explicit two-loop calculation in Chern-Simons fermion theory, and was more recently verified exactly in a large N in Chern-Simons scalar theory by Aharoni, Gur-Ari, and Jacobi by solving these Schrödinger Dyson equations. The theta naught here is precisely going to be identified with, in the duality with the Vasiliev theory, it's going to be identified with a parity violating interaction phase that I mentioned earlier. Now, the Vasiliev system can be generalized easily to the supersymmetric case, and also one can include Chern-Paton factors. So one can write down, in fact, arbitrarily supersymmetric extended, arbitrarily n-extended supersymmetric Vasiliev theory in ADS4. In the parity even case, with appropriate assignment of boundary condition, this could be due to free theory of some supermultiplets. Of course, in free theory, you can have arbitrary number of spin 3½ conserved currents. That's not very interesting. We know that with interacting conformal field theory, you cannot have arbitrarily high number of supersymmetries. In fact, well, as I mentioned earlier, Chern-Simons vector models are proposed to be due to parity violating Vasiliev theory. And it turns out that for this parity violating Vasiliev theory, the boundary condition always break higher spin symmetry. And it also will break some of the supersymmetries. It turns out that one can precisely identify the boundary condition that preserve 1, 2, 3, 4, or 6 supersymmetries in this supersymmetrically extended Vasiliev theory, and they can be matched to the appropriate Chern-Simons vector models, which are, of course, by now well known. This was demonstrated in this paper also from last week. I should mention that, let me make a few comments. First of all, Chern-Simons vector models, well, there's a rich zoo of Chern-Simons matter theories with different number of supersymmetries. But if you consider the case of Chern-Simons vector models, in fact, all these theories with different number of supersymmetry, very often they have the same matter content, but only differ by interactions in that they differ by some double trace or triple trace terms in the Lagrangian, or sometimes, let's say, going from some n equals 3 to n equals 4 or n equals 6 theory, you also gauge some flavor group with some Chern-Simons coupling. And all of these triple trace, double trace, or gauging of flavor group correspond to merely changing boundary condition of the bulk theory, but not changing the bulk Lagrangian. So there's a zoo of different supersymmetric Chern-Simons vector models that are due to the same supersymmetric higher spin gauge theory in the bulk, only with different boundary conditions, and they can be identified precisely. This is not quite a tautology. In fact, this proposed duality can be used to derive certain non-trivial relations among 2-point and 3-point function coefficients that are not yet known to follow from any symmetries, even higher spin symmetry. But I won't have time to explain this in detail. Now let me just summarize that chain of dualities through this what I call ABJ triality. We know through the work of ABJ, which generalized ABJM to n equals 6 Chern-Simons matter theory with UN times UM gauge group and Chern-Simons level k and minus k with some bifundamental matter content. So this theory is by now well known to be due to type 2A string theory in ADS4 times CP3 with some flat B field that is turned on related to a difference between the rank of the two groups. Now, I also argued earlier that in a different limit where you keep take n and k to be large, but with m regarded as with m kept finite. Now, this theory is more appropriately thought in that limit, more appropriately thought of as a Chern-Simons vector model with a flavor group gauge, but this merely corresponds to changing boundary condition for the dual gauge fields in the bulk. So, in fact, this theory viewed in a different limit is due to a supersymmetric version, supersymmetric and parity violating version of Vasiliev theory with some Chern-Paton factor and appropriate boundary condition in ADS4. And some precise identification of the parameters can be made. Now, this theory is holographically due to both a string theory and a higher spin gauge theory in ADS, and which suggests that this higher spin gauge theory and the string theory must be the same thing. This picture kind of emerges very clearly through this chain of duality. What happens should be that the bulk Vasiliev theory has bulk coupling, let's say called G squared, that goes like 1 over n. And it has a bulk nanobillard gauge group. So there's a bulk 12 coupling, which is not to be confused with boundary 12 coupling. These are completely different things. There's a bulk 12 coupling for this nanobillard high-spin gauge theory, which is m over n. And the Vasiliev theory is a good description in the weak coupling limit, where m over n is small. When you make m over n large, or let's say of order 1, then they cross over to a string theory. And the picture is going to be that the single string excitation generally correspond to bound states of higher spin particles, pictorially denoted in this way. So single higher, in this limit where you turn on, well, in this crossover where you turn on the bulk 12 coupling from 0 to order 1, the single higher spin particle turns into a leading radiation trajectory of string modes, whereas the bound states of some higher spin particles become a generic single string excitation. In this way, sort of you can build type 2A string theory out of this nanobillard supersymmetric higher spin gauge theory. Okay, now let me switch gear and talk about the ADS3 CFT2 story, which is equally rich. Now I'll backtrack for a moment. So ADS3 seems to be a lot simpler than ADS4. Gravity in 3 dimensions has no propagating degrees of freedom, for Einstein gravity. It's almost a trivial theory. And we also think we have a lot better handling on 2-dimensional conformal field theories than their higher dimensional analogs. But the story is not so simple. For instance, there are BDZ black holes in ADS3, and if 3D gravity is so simple, you should be able to quantize the phase space and identify the microstates of the BDZ black hole. Now, even with pure gravity in ADS3, one can ask the question, in fact, Witten asked this question a few years ago, whether the pure gravity in ADS3 has a CFT dual. And I would say that we still don't know the answer to this, largely due to our lack of understanding of irrational conformal field theories and our lack of understanding of the nature of non-perturbative effects in quantum gravity in general, despite some effort for a short period of time. Now, string theory admits ADS3 solutions, and sometimes we can have purely Neville-Schwartz backgrounds of string theory in ADS, which are exactly soluble on the world sheet. But the dual conformal field theory is not so simple away from the free orbital point. This problem appears to be more complicated than solving n equals 4 super-MLs at large n finite 12 coupling, because here there's not even any known integrability to help us on the CFT side. So it seems to be a pretty difficult strong coupling problem. Now, we know a lot about rational conformal field theories in 2 dimensions, and it will be desirable to have a gravity dual of rational conformal field theories so that we can compute things exactly and address questions about black holes and so on. Now, for this, we need to have a large n limit. In fact, this is a standard kind of objection for studying gravity dual of, say, a rational conformal field theory, because in a rational conformal field theory, the energy spectrum of states are evenly gapped, which naively prevents the possibility of thermalization behavior, which will be exhibited by black holes. But this could be, one could potentially get around this in a large n limit. You can imagine a large n limit, the gap between the states in the rational conformal field theory becomes very small, and which allows the behavior of thermalization, at least at time scale small compared to n, or some power of n. But for this, one not only need a family of rational conformal field theory with some parameter n, such that the central charge is large at large n, but one also needs the correlators to exhibit large n factorization, which is very non-trivial. This was a very clever and nice observation was made by Gabriel and Gavakumar. The data was run this in 2010, that the 2-dimensional version of the 3D vector model, I would say, is the WN minimal model. They further conjecture that this theory is holographically due to the ADS3 version of Vasiliev system, which I should emphasize that is not a pure high-spin gauge theory, but rather it describes an infinite tower of high-spin gauge fields coupled to massive scalars, in fact, 2 real massive scalars. Now, if one wants to construct a pure high-spin gauge theory in ADS3, well, it's not so hard to do. You can just take, just like at least at the level of classical equation of motion, one can formulate pure gravity as SL2 times SL2 Chern-Simons theory. One can formulate a pure high-spin gauge theory in ADS3 as SLN times SLN Chern-Simons theory with appropriate assignment of boundary conditions. So the resulting high-spin gauge theory is going to have spin S that runs from 2, 3, 4 all the way to n, where n is any number, any integer. Now, it's not clear whether the pure high-spin gauge theory in ADS3 by itself is well-defined number perturbatively and has a CFT dual. In fact, as I already mentioned, we don't even know the answer in the n equals 2 case, which is pure gravity. But Vasiliev system, on the other hand, is not a pure high-spin gauge theory. It contains an infinite tower, first of all, of high-spin gauge fields. As opposed to from 2 to n, it goes from 2 to infinity, and 2 real massive scalar fields. The high-spin interaction is controlled by the so-called HS lambda algebra, which I'm sure Matthias will say a lot more about in his talk. This parameter lambda is some kind of tooth coupling of the dual CFT. It also determines the scalar mass in the bulk theory. The dual CFT, which is the WM minimum model, is a conformal field theory. It's a rational conformal field theory that contains holomorphic and anti-holomorphic currents of spin 2, 3, all the way to n. It can be realized explicitly as a coset model, and is exactly solvable in principle. The primaries in the CFT with respect to the higher spin Wn algebra turn out to be labeled by a pair of representations of affine SUN, which I call R and R prime. So each primary with respect to Wn is labeled by a pair of representations R and R prime. The most basic ones will be you take R to be the fundamental representation and R prime to be the trivial representation, or the other way around, which I denote by phi 1 and phi 1 tilde. So if you take the OP of these, they generate all the primaries. The tooth limit is defined by taking n to large and this n over k plus n, which is defined to be the tooth coupling lambda, that is kept to be finite, and lambda is between 0 and 1. This lambda is mapped to a parameter of the conjecture dual Vasiliev theory in ADS3. One of the nice observations of Gabriel and Gaba-Kumar is that in a large n limit, if you take representations whose Young tableau do not grow with n, with some fixed Young tableau, then these primaries have a finite dimension in the tooth limit, which could be dual to elementary fields in the bulk. But the large n factorization is still non-trivial. The large n factorization in this context requires analysis of correlators. For example, what we normally call single trace and multi-trace operators in a gauge theory, well, in the general large n CFT, there's also a notion of single trace and multi-trace operators. They're distinguished by the behavior of, by the scaling of correlators with n. For instance, you have a 3-point function of single trace operator. Each single trace operator is the dual to an elementary field in the bulk. The 3-point function in this case will go like 1 over square root n. Whereas if you take a correlation function between 2 single trace operator and 1 double trace operator, then the leading Witten diagram in the bulk should look like this, and the 3-point function will be of order 1 as opposed to order 1 over square root n. So by looking at how the 3-point functions, let's say, of these operators scale with n, one can identify which are the single trace, which are the double trace or triple trace operators. And the answer appears to be quite non-trivial. Earlier, I said that each primary is labeled by a pair of representations, but not all of these are single trace operators. So not all of these are dual to elementary fields in the bulk. Some are bound states of multi-particle bound states in the bulk. So here in this table, I list there's a partial list of some single trace versus multi-trace operators. So these are labeled by Young tableau of the pair of representation. You can see that there's some kind of non-trivial combination that are single trace operators. This table is generated by explicit calculation of 3-point functions. And some other combination of these representations give multi-trace operators. Okay, so one of the puzzles with kind of peculiar and perhaps sometimes somewhat bizarre feature of this duality of Gabor-Diel and Gabor-Kumar is that in the dual CFT in the large n limit, even though some operators behave nicely in large n limit, there are also a large number of so-called light states. These are primary operators in the CFT whose dimension goes to 0 in the large n limit and form nearly a continuum in the large n limit. So there's actually a large density of states at low energy, which makes one worry whether large n factorization really holds in this theory. But the answer turned out to be yes, at least in the appropriate sense, provided that so the large n factorization in fact does hold for, as one can see explicitly by computing 3-point functions of these primaries, which are known, and they obey large n factorization provided that one makes the identification of single trace versus multi-trace operators as summarized partially in the previous chart. And also one sometimes have to make some identification which says that some descendants of these light states are related to double trace operators and so on and so forth. These have actually curious interpretation. In fact, I won't have time to elaborate on this much, but it turns out this kind of relations in the WM model is exactly analogous to the current non-conservation relation of the 3-dimensional Chern-Simons vector model. And the existence of these light states, in fact, implies a new hidden gauge symmetry in the bulk that are broken by the assignment of boundary conditions on the matter fields charged under these gauge fields. So it appears, in fact, that the holographic dual of the WM model is not just the Vasiliev theory in ADS3, but the Vasiliev system extended by infinite tower of additional elementary massive matter fields and hidden Chern-Simons gauge fields in the bulk. So it's actually a much more complicated theory, which we don't really know explicitly how to write down such the equation motion for these theories in the bulk, for instance. However, there's, let me just backtrack for a second. There's some more conservative statements one can make. So the Vasiliev theory in ADS3, as I mentioned already, contains gauge fields of spin 2, 3 all the way to infinity, and a single complex or 2 real massive scalar fields, which are called phi. So this phi must be due to one of the 2 basic primaries, which are called the phi 1, phi 2, phi 1, phi 1 tilde earlier. Either this box 0 or 0 box, both, each one of these is a complex scalar operator. So one can propose a perturbative version of the Gabor-Diel Gabor-Kumar duality, which appears to be true to all order in 1 over n. That is, Vasilyev's system in ADS3 is dual perturbatively to the subsector of the WM model that is generated by primaries of the form R column 0, where you take one of the rotation to be trivial, the other one to be non-trivial. This subsector would not make sense at finite n, but it does make sense at infinite n and to all order perturbatively in 1 over n. So it closes, the subsector closes perturbatively in 1 over n to all order on the sphere. So it defines the consistent CFT perturbatively in 1 over n on the sphere, but it's not modular invariant and it's non-perturbatively incomplete. At least this perturbative version of the duality with the Vasiliev system seems that it's likely to be true exactly, at least perturbatively to all order in 1 over n. But as I mentioned earlier, the full non-perturbative dual of the WM model still seems to be complicated. That is some kind of bizarre extension of Vasiliev system which we know very little about. It would be nice to know the precise dual of the full WM model because this is a unitary large n conformal field theory which we can solve exactly for any n. In particular, we can compute things like the thermal 2-point function of the theory, which is expected to measure the response of a black hole in ADS3 to some external perturbation. It'll be nice to know exactly. Now, I think Matthias will elaborate on this. There's an alternative proposal of potentially non-perturbative duality, but involves a non-unitary CFT. That is, you can take WMino model, but make a continuation of make any continuation of a different kind. So the lambda, which was dual coupling, was restricted between 0 and 1, and correspondingly, the dual higher-spin gauge theory involves HS lambda algebra. But if it actually analytically continues, the higher-spin symmetry algebra lambda to n, then HS n is essentially reduced to SLn. And in fact, we know that the WMino model involves higher-spin currents up to integer n. There's an alternative, this kind of analytic continuation where you want to consider a alternative limit where you keep n finite but take the central charge to be large. This will take you to non-unitary theory, but nonetheless you can compute correlators exactly. Now the spectrum looks somewhat different in this very different limit. For example, these two basic primaries, phi 1 and phi 1 tilde, I mentioned earlier. Now one of them is still dual to an elementary field in the bulk, but the other one becomes non-perturbative in this limit, which are presumably identified with the conical surplus in SLn times SLn higher-spin gauge theory, as was recently discovered by these authors. Now, both of these have negative energy in the bulk, and the CFT is non-unitary, but nonetheless, there's the intriguing possibility that this duality is exact, and that Vasiliev system analytically continued to lambda equals n is complete quantum theory by itself, though non-unitary. Okay, I will say a few words about black holes in higher spin gravity. There's more understanding with the ADS3 case because the pure higher spin gauge theory, at least it's a little simpler. There are higher spin black holes that can be constructed by different ways of embedding SL2 into SLn. One can construct black holes that carry a higher spin charge, but these higher spin black holes are kind of subtle because the metric is not a gauge invariant concept in higher spin gauge theory, and sometimes one can perform gauge transformation that turns the horizon into a geometry without the horizon. What exactly should be called a higher spin black hole is a bit tricky. One can come up with a gauge invariant characterization of these, which we might hear more about in other talks. It was also shown that the entropy of these higher spin black holes is consistent with the higher spin generalization of Cardy formula on the CFT side, which are computed from the partition function of the CFT with the additional chemical potential for higher spin charges. The higher spin black holes in ADS4 is less understood. There's a class of solutions found by Didenko and Vasiliev and generalized by Yaziola and Sandel. But the interpretation of these are not clear. In fact, it's not even clear whether these are truly black holes because of our lack of understanding of gauge invariant characterization of the horizon of these black holes. In fact, from the CFT side, it seems to be unlikely that there should be any dual black holes, at least for the dual CFT on the sphere. But there's some recent new work that indicates that the CFT has some rich structure. These Chern-Simons vector models have some peculiar structure if you put these on Riemann surface of genus greater than 0. In fact, these, if you put the Chern-Simons vector model on Riemann surface of genus greater than 0, these theories have a spectrum that is reminiscent of the spectrum of WMino model, that there are this large degeneracy of light states. And perhaps this will have something to do with higher spin black holes with non-trivial horizon topology, which remains largely unexplored. Just say a few words about DSCFT, which Andy Struminger has already talked about yesterday, just to summarize a few points that Vasilyev's higher spin gravity theory can also be defined in de Sitter 4, which is conjectured to be due to some ghost-like SPM model. And one can compute some fun things like exact wave function of the universe from the partition function of the dual CFT, which is in principle, which is simple. Now, it remains to be seen whether this toy model for DSCFT can really help us to address standard puzzles with de Sitter holography. There are many open problems on the subject, too many to list here. I'm just going to point out two of them, which I thought are worth exploring. One of them is that even though I mentioned that the higher spin gauge theory due to ABJ theory cross over to a string theory, I don't exactly expect the closed string field equation classically to reduce to a Vasiliev equation in the appropriate limit, because there isn't a one-to-one correspondence between closed string states and higher spin one-particle states. Rather, single closed string states are due to multi-particle bound states of higher spin particles. But there's some alternative construction was first proposed by Jeffers and Gayato. That is, you can engineer a Chern-Simons vector model actually by putting D6 brane inside the RP3 on the RP3 inside the CP3 in ADS4 times CP3, and in the zero radius limit with some flat B field, this will be due to a Chern-Simons vector model as well. And this I actually expect the string field theory on these D6 brane to reduce in the zero radius limit to precisely a supersymmetric version of Vasiliev theory. Of course, this remains to be shown. It will be very non-trivial to demonstrate this. Presumably requires using pure spinor formalism, but it will be fantastic to demonstrate this at the bulk level, and perhaps we can learn some lessons about how to formulate closed string field theory. I think one of the in retrospect, it's not really surprising that these vector models are due to higher spin gauge theory, which what was surprising is that Vasiliev actually told us how to write down this equation of motion explicitly in the bulk, and this could be useful. And of course, one would like to see if we can learn some useful lesson from higher spin black holes about black holes in semi-classical gravity. And the general lesson is that, well, it's useful to explore limits of theories that exhibit hidden symmetries, and we know very well examples involve supersymmetry and conformal symmetry, and now also by exploiting higher spin symmetry, it seems that we can get some mileage out of this and understand use it to understand the structure of the ADS-CFT correspondence. So I'll stop here. Thank you.
Thank you very much. Questions and comments? Yes, Andy?
So in the bottom line of that ABJ triality, you had a relationship between the higher spin theory and the 2A theory. So how does it become, so the left-hand side is non-local on the ADS radius, but the right-hand side is local?
Yeah, so
just so let me, how does that happen? And also, is the graviton the same thing on both sides?
Not quite. So on the, sometimes yes, because sometimes yes, but on the left-hand side there's also color gravitons. Those will confine in the strong total coupling limit. You won't see them on the right-hand side. So I would think of these strings as emerging out of the flux tube of the non-abelian. Well, the string sort of is heuristically thought of as a flux tube of the non-abelian higher spin gauge fields, in much of the same way that we think of the QCD string, but in this case, the string theory lives in the same dimension as the higher spin gauge theory, as opposed to one dimension higher. But I should mention that I mentioned this other construction, which involves wrapping D6 brane on ADS4 times RP3 inside this geometry. In that case, which is different duality. In that case, I would expect is the open string field theory on the D6 brane to reduce the Vasiliev system. So that's a little different. In that case, I actually expect literally the open string field theory to reduce to precisely Vasiliev theory and nothing more. Whereas in this case, the closed string field theory is should not be the same as the Vasiliev theory at the classical level, because the correspondence is such that the single string states are due to multi-particle states in the Vasiliev theory side.